recording here. See if anyone else is on. All right. Where were we here? I think we'll go here. So last day we got through section 1.1, and today we're going to pick up the pace a little bit. Nothing too crazy, right? I do have more handouts for section 1.3, and I have 2 leftover handouts from 1.1 and 1.2. And if we need more, does anyone need section 1.1 and 1.2? Well, this is all good. Okay. 1, 2. 1, 2, 3, 5. Does anyone need paper to make a name tag so that I can see your names? Thank you, Anderson. Thank you, Chloe. Yeah. All right. It's still hard to see on here. Oh, 1.2? Yeah, you got it. And that is yeah. Right. Let's see here. So, start a new one here. Yeah, oops, 120. Recalculus. All right. I changed some things in WebAssign, and it did worry some people. Hey, this is past due. And one of us had already done it, but I transferred your grades, so don't worry. So what I decided to do was, it's a little bit hectic to do the problems beforehand, and obviously that would be the best way to do it. But what I've decided to do instead is, I'll just show you, where were we here? So many tabs, it's crazy. Oh, here maybe. So if we log into WebAssign, I'll show you how it looks on your end instead, because it's way nicer on your end than on my end. So now you should just have quizzes for each section. Okay? And so what I've decided to do instead was, okay, well, these will be your assignment marks, right? They're called quizzes, but I mean, that's just what they're called. And they're all due January 31st at midnight. Okay? And so as we work through these, I want you to kind of stay on top. You're welcome to leave these to the last minute. I wouldn't recommend it, right? So they're all due January 31st. And so last day we did 1.1, right? We're going to get into 1.2. And so as we kind of plow through these, you can work through these quizzes just to make sure that you're staying on top of things, right? And so I picked this due date because that's a week after we're supposed to have finished chapter 1. right? And so after we've gone through all this material, right, then you'll have a week to finish all these quizzes, right? But if you're doing 1 or 2 kind of every day, then that's going to be a lot easier. Okay. Roughly, each quiz should take you about half an hour, right? Roughly. Some take more, some take a little bit less. But just so you have an idea of kind of what you're getting yourself into. You can definitely start a quiz, save your work, come back to it, right? And so, so that will be all safe. So that's how we're gonna do it. So all the chapter will be due on the same day, but as we work through it, right, you can work through those quizzes, right? And those will be your assignment marks. So what I haven't posted here is I will also, because I wanted to warn you guys beforehand, there will also be what will be called homework. And so those are not for marks or anything. Those are just extra problems, maybe a little bit more involved problems, right? That you might have to think about a little bit more. And those are just for extra practice. And so those will just always be open and available to you, and you can work through them. And if you want more practice, then that's a really good place to go, right? Because it has, you know, sometimes it'll have like, hey, watch this video instead, and here's a problem that we solved that's similar to the one that you're trying to solve, right? And so it's just a better experience. And so so those I will post, but like I said, I didn't want to post them now and everyone's freaking out. There's so much homework, right? So these are called quizzes. Those are for marks. The homework, not for marks, right? Just for practice. Yeah. So on WebAssign, each section has a quiz which will count as your assignment mark. Okay. I will also post homework. I will also post homework. I think it might be abbreviated HMWK, but you'll figure it out. So I'll also post homework on WebAssign. Oops. But these are not for marks. And I'll underline that, not for marks, just for practice. Confusing with our stray red line on the, but, okay. Any questions about that? So you'll have the quizzes, those are for your assignment marks, and then the homework, just extra practice, right? If you feel like, oh, 1.1, that was easy, right? But maybe 1.3 was hard for you, right? So then maybe try the 1.3 homework and have those extra problems to work through, right? Because as much as we don't like to do work, no one likes to do work. I don't. Okay? That's the only way that we're going to learn this stuff, right? Working on these problems, figuring it out, right? And so it's our only thing that we can do. Okay. All right. So let's start 1.2. Where did I put it? Oh. Here maybe. Yeah. So section 1.2 is about exponents and radicals. And so, and you've got it in front of you, so I can just blow it up here. Right, but just some notation and just kind of fun facts. It's still really bright on here. Should I turn? Do you guys mind if I try that? Is that a little bit better? I don't know. It's so weird. It feels like the sun is just coming in right here. Usually that's nice. But not when we're dealing with this. So anyways, so an exponent, right, or exponential notation is just when we have a times a times a times a, right, we can shorten that to a to the power of n, right? And so whenever we're dealing with an exponent, right, we're gonna have a base, and the base is this a. Okay? As a fact, anything to the power of 0 is 1, right? So that's something that we'll have to keep in mind. Right, anything to the power of 0 is 1. And usually this one, a to the negative n, can be rewritten as 1 over a to the power of n, right? So if you have that negative power, that negative exponent, it brings everything down to the denominator, right? Usually how I end up using it, right, most often, is going from here to this. Right, because usually I want to bring this up to the numerator to be on the same playing field as all my other numbers, or all my other variables. So, exponents. Talk about the laws of exponents. And these, unfortunately, I hate to say it, but these are just, if you don't have them memorized already, it's time to memorize these guys. Okay. So I'll zoom in even more. There's the explanation on that handout that I gave you, right? But let's just talk about these different laws. And so as long as a and a, right, these are the same base, so that's important. Right, if we're multiplying the same base, then we can combine them by adding the exponents. Okay. Same thing if we're dividing, right? Then we can subtract the exponents to combine the a. Notice that these, right, are the same base. So that's going to be really important. Right? It assumes that we have the same base. If we take the power of a power, we actually can just multiply them. Right? And so that's what we're seeing here. Sometimes a little trick is to rewrite a to the power of 4, for example, right? 4 you can rewrite as 2 times 2, right? And so what we can do is we can go from here, a to the power of 2 times 2 can be written as a to the power of 2 to the power of 2, right? So sometimes we have to work backwards, right? And same thing here, right? Whether you want to combine a and b, right, because they have the same power, right? So now the bases are different, but the power is the same. You can combine those, right? A times b all to the power of n. Or if you want to look at it this way, well, if you're multiplying two things inside here, then what you can do is you can bring that n inside, right? So that only works if we're multiplying or dividing, right? So that's the next law. So if we've got to the power of n here, then, and we're dividing, right? Dividing and multiplication behaves almost the same way, right? So you can bring that n inside onto both of them, right? Or the other way, if you've got the same power, you can pull that power outside, right, and have a over b to the power of n. Same thing, right? So now we've got a negative exponent, negative power, right? And so what happens would be, well, if we brought in this a to the negative n, right, and b to the negative n down here, Well, the negative b to the negative n, if we had to rewrite it, would be b to the negative negative n, right? Brings that up top. A to the negative n brings it to the bottom, right? And so that's why they switch. So now we have b over a all to the power of n. Same idea, right? This one and this one are just very similar, right? But now we've got different powers, so negative n and negative m. Well, b to the negative m, we can rewrite as b to the m, right? B to the negative negative m. Right? And then a to the negative n, if you bring it to the bottom, right? A to the negative negative n, and that's where you're at. So those are the rules of the game, right? So let's play the game. Now for this one, for section 1.1 and 1.2, we're still trying to figure out how I wanted to tackle this class. And so I didn't have the exercises built into the notes, but you'll see for 1.3 onward, right, the questions that you're about to do are inside the notes. And to motivate you a little bit, a lot of the test questions will be pulled exactly from these blocks that I give you. Okay? And so if you've worked through, and there are a lot, right? But if you work through all the exercises that I have kind of put up here on the board in class, then you will have seen a lot of the test questions. Okay? Maybe not 100%, but I'm going to go with 80% of the test. I'll just pull questions from these exercises, right? And remember that I post these notes. So for section 1.1 and 1.2, right, I've posted the ones from class on Moodle, so it might be worth checking out. But from 1.3 onwards, where did I put them? Right. The exercises that I expect you to be able to do, right, are just built into the notes. There's a lot, but at least it feels more manageable, maybe, or hopefully it feels more manageable, right, or doable. All right, so if you were me and you were making a test, which one do you think, you could only pick one, let's say, which one would you pick? I don't know, they all look the same to me. Right? 31, B, you got it. Let's try it. Could be any, but let's try it. 31B. So I always want you to, when you know the questions that I'm choosing from, right, you want to think, okay, well, which one do I think she's going to pick? So let's do 31B. Let you try it first. I put another one on the list. 32C. Dun, dun, dun. Okay. So let's see what we ended up with here. So if we're looking at 31b, sorry, we've got w to the -2, w to the -4, and w to the power of 5. All of these have the same base, right? And so if we have the same base, then the first law of exponents says that I can just add these powers, right? And so now I've got w to the power of -2 plus -4 plus 5, right? Usually I like to do the plus -4 instead of skipping straight to -4. But if you want to skip straight to -4, that's fine. I just want to show where it's coming from. Of course, that's my job, right? So if we have w to the -2 plus -4, so -4 minus 6 plus 5, I get w to the -1. Brought a calculator today, just to make sure. Don't try to be a hero. Check with your calculator. So.
And would you leave it like that, or would you want it to be positive?
Let me see here. Let me make sure I did the math right first. I did. So then simplify each expression and eliminate any negative exponents. So negative exponents, well, I can rewrite this as 1 over w to the power of 1, which I'm just going to dissolve. All right. Nice. How about the one I added, 32c? Oops. Y to the power of 7 times y to the power of 0 all over y to the power of 10. There's a couple of things that we need to tackle, right? The y to the power of 0, we know anything to the power of 0 is just 1, right? And so first thing I'm going to do is I'm going to have y to the power of 7 times 1 over y to the power of 10. And of course, I'm showing way more work than you might need to, right? You don't have to show the times 1. And then we'll start from the get-go, right? You're going to try to stack your equal signs as much as you can, right? Unless you run out of room or things get weird, right? But whenever you can, stack your equal signs, right? So it looks nice and clean. So we can rewrite this as, okay, well, the y to the power of 10, I can bring up from the denominator by making the power negative. So I get y to the power of 7 times y to the -10, right, times 1, which I've taken care of. I've got the same base. So now I've got y to the power of 7 plus -10. So I get y to the -3. If I have to get rid of all the negative powers, I get 1 over y to the power of 3. Nice. Any questions about those? So give those a go, maybe later, and I'll give you, oops, some more there. Let me just check. Did I have more? Oh, I did. These ones are a little bit bigger. Right. But again, you're going to simplify each expression and eliminate any negative exponents. And so what if we had to do something like 41a? Right, just picking one. So I'll underline it. Try 41A. So for 41A, there's a lot going on, right? We've got different bases, and we've got that 8/2, right? And so one thing to keep in mind is that as long as we're multiplying, right, inside, and there's no addition or subtraction, then how you want to cancel things, it will work, right? It's as soon as we're doing adding or subtracting in there, that canceling is going to be a little bit harder, right? So if we have 8a to the power of 3b to the -4 over 2a to the -5b to the power of 5, that's where we started. That 8 and the 2, right, we can deal with those right away, right? Because what we can do is we can just say, okay, well, I can rewrite this as 8/2 times a to the power of 3b to the -4 over a to the -5b to the power of 5. I'm allowed to do that, right? Because I'm multiplying, and so I'm allowed to separate them. And because we know that multiplying fractions, right, we just multiply across. And so I can easily smush them back together. And so if I separate them and just to look at them like this, well, 8 divided by 2 I know is 4, so I can replace that term by 4. And so now I have 4 times, should we do it all in one step? Bring the a to the -5 and the b to the power of 5 up to the top. Let's do it. So a to the power of 3, b to the -4, bringing the a to the -5 up to the top, right? I get a to the -5 times b to the -5. Bringing all those guys. And I just think of it as them all being on the same level now. Right? So if we regroup these, then I've got 4, which is just going to hang out on the outside. Right, it's not really doing anything. 4 times a to the 3 and a to the -5, and then b to the -4 and b to the -5. Right, so remember to combine your exponents, they have to have the same base. And so I'm going to regroup these so that I have the bases of a together and the bases of b together. Right, just showing that extra step, but I think it's worth it. 4 times a to the 3 times a to the, and I'm just going to do -5 is just 5. Right? Times b to the -4 times b to the -5. So now I get 4 times a to the 3 plus 5 times b to the -4, oops, -4 plus -5. So I get 4 times a to the power of 8 times b to the negative 9. We're supposed to eliminate negative exponents, and so I have to move that b to the negative 9 down to the denominator, and so where I end up is at 4 times a to the power of 8 over b to the power of 9. Nice. That one's a little bit more work, right? And you can see that all of these are a little bit more work here.
Is it okay to just work it in columns, like just go 8 divided by 2, you get 4 on top, and then do a to the third divided by 8 to the negative 5, and then you get the 8 to the 8 on top, and then
Can do that.
Okay.
Totally. Yeah, there's lots of ways that we could go about doing it. And if you find a way that you like, right, whether separating them into columns like that, right, and just kind of dealing with them with the same base, right, that's totally fine. Or I always like to bring them up to the same level and just kind of cancel that way. But if you find a way and it follows the laws of exponents, you're safe to do that. Okay? And so as long as you get to the same answer and it's all legal moves, you're fine. Right? So, good. You guys used scientific notation before? No? Okay. So scientific notation is usually used if we have to express numbers that are really, 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 really big or really, really, really small, right? So if there's lots of zeros that we have to deal with, then we usually use scientific notation. And so I'll just add in a little note here before we talk about scientific notation. So for numbers that are very large or very small, we can use scientific notation for any number, but we definitely use it for very large or very small numbers. Okay. We use scientific notation instead of the actual number. Instead of the actual number. So scientific notation, you're going to take the number, right? So if we're talking about maybe something simple like 3,000, right? Then you draw it down to just the number 3, right? And 3 times 10 to the power of, and then I imagine moving my decimal, right? 1, 2, 3 to the power of 3. And so, for example, if x is, let's do 30,000 instead. And I use commas to separate my thousands, right? So every 3. So now, what we do is we imagine this decimal here, and we have to move it 1, 2, 3, 4 to cut it down to be just 3. And so here, this is 1, 2, 3, 4. So what we write is that x is 3, and just to emphasize, I do 3.0, depends, but it's just 3 times 10 to the power of 4. So you want to chisel it down until you have just the number, right? And it's just one number and then a decimal and then whatever decimal places. So for example, if x is going to be 0.00129, right? Now we're moving the decimal the other way, right? And so now we do, instead of to the power of a positive number, right, then we do to the power of a negative number, but moving the same direction, right? And so from this actual decimal, we have to move 1, 2, 3. Oops, should have stopped at 3. 2, 3. Because scientific notation says that, okay, well, we can only have one whole number, and then the rest is followed by the decimal, right? And so what we have is we have -1, -2, -3. So x is going to be 1.29 times 10 to the power of -3. So the power is just going to be how far has that decimal moved, right? In the negative direction or kind of into the zeros, right? Or moving up, which I would call the positive direction. The key is that these numbers here before the decimal has to be a number between 1 and 9. Why can't it be 0? Because if it's 0, you could move the decimal one more time, right? And so it should be between 1 and 9. Hey, it's already on here, right? Where a can be 1, but has to be less than 10. And so the number must be between 1 and 9, is what that says. Oh. All right. So let's deal some exercises here. Okay. Oops. So from this first little section, right, we can start out and we can reverse these numbers out of scientific notation into an actual number, right? And so I want you to try 85D and maybe 85A. Why not? 86A is way too big. It's like 14 zeros potentially. No thanks. So if I'm starting with 85A, then I want to convert 3.19 times 10 to the power of 5 into just a number. So that's going to be 3.19. And then you can imagine reversing this decimal, right? It had to move out 5, so I know it's going to be a big number, not a small number, right? And so now I have to move this 1, 2, 3, 4, 5. So everything in there is going to be zeros. Which is going to be 319,000, 319,000. How about for 85D? We've got 9.999 times 10 to the negative 9. So many nines. Right. And it's going to be a lot of zeros, right? Because now we had to move 9 into the kind of, into the smaller side. So now we have to move 1, 2, 3, 4, 5, 6, 7, 8, 9. Yikes, for that decimal. So I can write that as point. So 0 point, and then 1, 2, 3, 4, 5, 6, 7, 8. Right. And that last one is going to be that digit in front of the decimal. Right. And then followed by, because now there's no decimal there anymore, right? Because we've moved that decimal to where it should be. And then followed by 3 more nines. 1, 2, 3. The rest on here are just more examples, right? So again, like we were doing earlier, just converting these big numbers or really small numbers into scientific notation. Right? One thing that I want you to have a look at though, so I'll leave you to do those later, but usually your calculator will give you scientific notation if the number is really big or really small, right? So if we try something like 100 times 30,000, mine can still handle it. Make it bigger. How about 9,000 to the power of 100? Math error.
This is overflow error.
Mine gave me an error too, even though I know this one gives me scientific notation, so I'm not sure why. Maybe do something more reasonable. 100 to the power of 25.
30.
And then it gave you scientific notation?
Yeah.
Nice. So it will give you scientific notation. Sometimes it just can't handle the numbers, I guess, if they're too big. So if you do, or if I did 100 to the power of 25, it gave me 1 times 10 to the power of 50. Right? And so just being able to recognize how your calculator gives you scientific notation, because sometimes it'll use a little e, right? And so sometimes, so on your calculator, right, try something like 100 to the power of 25, right? And so my calculator shows 1 times 10 to the power of 50, and that's actually what's on my screen, right? Sometimes, but I don't know if everyone has their calculator here. I've been forgetting mine, so I can't blame you. But sometimes it might show something like 1E50 for some reason, right? So some calculators just show scientific notation differently, right? And so some calculators show, and I'll clean up this 50 here. 1e 50, oh, try to at least. Right, it just depends on what's going on. And some calculators are just really subtle about it and just say 1 with a space and then 50. Less clear, right? So that's what I mean. You want to get to know your calculator and know when it's showing you scientific notation, because it can happen, and just be able to recognize. So let me know if your calculator, when you try it, shows anything other than those. The second one, it's showing the E. Yeah. So that one's pretty common. This one I really don't like. I find it really confusing, right? But just be on the lookout so you can give it a try. Nice. All right. Oops. Keeps taking me back. Yeah. So because I want to move on, I'll leave these for you to do, but these are just going to combine your laws of exponents with scientific notation, right? And so you're going to simplify these and say your answer rounded to the number of significant digits indicated by the given data. We're not going to bother with significant digits or sig figs, significant figures. And so don't worry about significant digits, also called significant figures, sig figs. There's lots of rules for sig figs as well. And definitely if you're in chemistry, for example, they really care about sig figs, right? Because we're measuring things, and so sig figs will be really important. But just for this course, nah, right? But just know that you could take it up a level and use sig figs as well, but we won't. Okay. Good. Any questions before we start talking about roots or radicals? Nah. So if we're taking the nth root, we show it by, oh, there we go. We show it by putting the n inside the hook of the root, right? And so from here, oops, what we can say is that, well, okay, if the nth root of a is equal to b, right? But let's say, for example, I'm trying to solve for a, then how I undo the root, the nth root, is I have to take the nth power of both sides, right? And so to undo the root, we have to take the power, the power of that on both sides. Okay. And so remember to take the nth root of a, we write a to the power of 1 over n. And so the nth root of a is equal to a to the power of 1 over n. And that's just a rule that I'm confident we established in one of those rules that we talked about. Right. And so to get rid of that root, right, what I need to do is I need to take the nth power of both sides. So if the nth root of a is equal to a to the negative n, or sorry, not negative, a to the 1 over n, that's the truth. But if that's equal to b, right, just some value b, then to get a on its own, right, I need it to the power of 1. So what I can do, remember the laws of exponents says that if you take the power of a power, you just multiply those powers, right? And so if we take a to the power of 1 over n to the power of n, whatever I do to one side, I have to do to the other side, right? So now I have is b to the power of n. I'm using brackets to show that these things are one item. Well, this is the same as a to the 1 over n times n, which is b to the power of n. A to the 1 over n times n, we can rewrite as a to the n over n, which is b to the power of n. N over n is 1, and so that's how we undo the powers. So a to the power of 1 is b to the power of n. Are you guys okay if I use the therefore? This means therefore. Saves us a lot of writing. Therefore, a is b to the power of n. I'll just make a note here. Therefore. Okay. So to undo, right, or to undo or unravel or just kind of take the inverse of later on. So to undo an nth root, we raise both sides to the power of n. Okay. So let's just talk about, again, some properties of these roots. And the reason we have to spend time talking about them is because once I introduce them, I expect you to have them in your mind, right? So some properties, right? Just like the powers, right? The roots are essentially powers, right? Remember, if we have to take the nth root, we just take to the power of 1 over n, right? So it behaves the same way as a power. So none of these should be very surprising, right? If we've got a times b under the nth root, we can split them up because we're multiplying inside. we can split it up as the nth root of A times the nth root of B. Usually, same idea as before, right? Usually we're moving from this to a combination, right? But it just depends on what we're working on. Same thing, because we're dividing, right? So it only works if we're multiplying or dividing, right? But if we're dividing in here and we're taking the nth root of all of it, then we can take the nth root of each of the numerator and the denominator individually. Same thing here, right? If we're taking the mth root of the nth root of A, right, then you can rewrite the nth root of A as A to the 1 over n, and then all that is to the power of 1 over m, but now you're multiplying powers, right? And so now you have A to the power of 1 over n times m, which is the same as the m times nth root of A. The tricky part is that the root behaves differently depending on if the root is even or odd. Right? And so if the root is odd, right, 1, 3, 5, whatever, then if you take the nth root of A to the power of n, it's just going to be A, right? And so that's how you kind of get rid of that root. However, if n is even, right, the square root, the fourth root, the sixth root, then if you take the nth root of A to the power of n, it's just going to be the positive value, right? And that's because if n is even, right, if you square a value, it loses its negative. If you take the power of 4 of a value, it loses its negative, right? And so now it's just going to be able to return the positive value, the absolute value of A. Right? Let me see here. P. All right. Which one are we going to do here? 47B, you got it. Nice choice. Is that the one you said? It's the one I was eyeing up, actually. Even if you're not quite done, we'll start tackling this bad boy here. So 47b, oops. We have got the third root of a squared b times the third root of 64a to the 4 times b. There's lots of different ways that we could take this, right? First thing I'm noticing is, well, they're both taking the third root, so I could just put them over a combined root, right? And maybe that's, I don't know, is that what we want to do? What's another option we could do? We could bring that third root inside, right, on all of these, which we'll probably end up doing anyways, right? So it just kind of depends on how we want to approach this. So what do we want to do? We've got choices. So just to show that we can combine these, right? How about we put them all under the third root, right? And so now we can combine these and say, well, I'm taking the third root of a squared times b times 64, oops, 6 times 4 is not 64, times 64 times a to the power of 4 times b. So now probably what I want to do is I want to simplify inside here, right, before I keep going. And it's safe because I'm just multiplying inside. And so now I've got the third root. If we move a little bit faster, is that going to be okay if I move the 64 out front, right? Because I usually like to have coefficients and things like that out front. And so I've got 64 times a to the power of 2 plus 4, right? Combining those bases of a right away. You could do that in an extra step, that doesn't matter. But I'm just going to do it in one step now, times b to the power of 1 plus 1. Usually I want to check to make sure that I've got all the terms in there, especially when there's quite a few, like here, right? And so what I've got is, I'm just leaving that third root on the outside, and I've got 64 to the power of a to the power of, times a to the power of 6 times b to the power of 2. Now, what I'm going to do is I'm going to bring that third root inside, right? And so I could rewrite it as, because I'm multiplying inside, I could take the third root of 64 times the third root of a to the power of 6 times the third root of b to the power of 2, right? Or I can just do something like this. So I've got 64 times a to the power of 6 times b to the power of 2, and that's all to the power of 1 over 3, right? That's replacing the third root. It's doing the same thing. So now by the exponent rules, right, I can bring these on, the 1 over 3, I can bring it on to each of these terms. And so, but if you wanted to keep it and treat it as the root 3 still, that's fine. So 64 to the 1 over 3 times a to the power of 6 times 1 over 3 times b to the power of 2 times 1 over 3. I'm going to try 64 to the power of 1 over 3 because maybe, just maybe, it's a number. It's 4. What a surprise. Make sure that you know how to do that on your calculator, right? So 64 to the power of 1 over 3, you might have to put the 1 over 3 in brackets, because otherwise it might do 64 to the power of 1 and then divide it by 3, It just depends on how clever your calculator is, right? And so, so make sure that when you do 64 to the power of 1 over 3, you get 4. Or maybe it'll let you take the third root, right? But just in general, we need to know how to do that. And so, and then a to the power of 6 times 1 over 3 is the same as 6 over 3, right? 6 over 3 is 2. A to the power of 2. And then we've got b to the power of 2 over 3, which we can't simplify more than that, right? And so what the instructions said was just to simplify the expression. I would say leaving it as b to the power of 2 over 3 isn't quite simplified. So I would probably rewrite it as the third root of b to the power of 2, but they're equivalent, so yeah. So do you mean this one here?
Yeah.
So this 1 over 3, this exponent, because we're multiplying inside here, we're allowed to bring it on to each of them. So here we have 64 to the power of 1 over 3. Here we have a times, or a to the power of 6 times 1 over 3. And here we have b to the power of 2 times 1 over 3. And so the 64 to the 1 over 3, if you do it on your calculator, works out to 4. So just make sure that that's what you get when you do it. You might have to put brackets around the 1 over 3.
You can also do like the cube root of 64.
Yeah, if your calculator is clever. Hmm?
Oh, cube root, yeah. Okay, fine.
Aha! That'll do ya. Yeah, you want the third root. Good. Yeah, so again, kind of get used to your calculator, right? See how it behaves, right? You might have to put brackets around, or it might just do the third root for you. This one is fancy enough that it'll just do any root for you. So you don't even have to use the shortcut. All right. So I would rewrite this as 4a squared times the third root of b to the power of 2. But they're equivalent, so I would accept either of those two answers as being simplified. Right? But there's no further that we can go. Okay. Any questions? Uh-huh. So we just worked with them, but rational exponents is when we have things like a to the power of m over n, right? Now we've got a to the power of n under the m under the nth root, right? And so we need to be pretty comfortable moving between each of these kind of notations, right? So if you have a to the power of m over n, then you should be able to rewrite it as the nth root of a all to the power of m, or the a can move inside the nth root, right? And it'll still be the same. Okay. Which questions did I just give here? Radical expressions. So I'm just going to bring two sets of problems in here. 3 sets of problems. Man, there's a lot. Let's practice, you know what? We just did the third root. How about we do 77b? So the goal is to simplify and eliminate any negative exponents. So at the end, we should not have any negative exponents. Okay. So I'm going to give myself a bit of room here. 77b is the square root of 16u to the 3 v over u times v to the power of 5. So again, it's up to you if you want to break up that square root. Remember, the roots behave in such a way that if we're dividing inside, then we can split the roots up, right? If that makes it easier for you, right? And so part of our skills in this course is going to be knowing what we can do and also being able to see what's going to make it easier for us later, right? And so for now, I don't really see an obvious choice, right? But if you had something like maybe just 16 up top and not the u to the power of 3 and then v, right? Then you might want to split up that square root and just take the square root of 16 and that's done. And then focus on the denominator, right? The bottom term. And so for now, I'm just going to leave everything under the square root. But what I will do is I'll bring everything from the denominator up top, right, by using the negative exponents. And so I get 16 times u to the power of 3 times v times u to the negative 1 times v to the negative 5. And that's all under the square root. And usually, this is, I don't know, just me being, but it's good to know these things, right? And so usually at the end of the square root, unless it's not terribly important, right? But if you're writing another term after this, it's nice to show where the square root ends. So I just do a little, hey, this is where it ends actually, right? And then we can do ×3 or something like that on the outside, right? And it'll just be more clear where it ends and where it starts. It's pretty obvious, square root, right? But where it ends might be a little bit helpful to know, right? And so I'll do my best to show you all these tricks, right? So that when you go into calculus or whatever math course you take next, you'll look like a pro, all right? So leaving the square root or just kind of ignoring the square root for now, I'm going to simplify, right? I've got the base of u and the base of b that I can simplify, right? And so I've got 16 times u to the power of 3 plus -1 times v to the power of 1 plus -5. Which I get 16 times u to the power of 2, v to the 1 minus 5, v to the -4 square rooted. I drew over my numbers there. We've got a couple of options, right? Because we're multiplying inside, right? Multiplying and dividing, we're allowed to split up the square root and do whatever we want. And so, well, I could rewrite this as the square root of 16 times the square root of u squared times the square root of v to the -4. I can do that. Only because I'm multiplying, right? Not adding or subtracting. The square root of 16, right? Just make sure that you know how to take the square root on your calculator, but also, again, don't be a hero. But it is 4, just like you thought. The square root of u squared, we probably just know is just u, right? But the reason is because we can rewrite the square root as u to the power of 2 over 2, which is u to the power of 1. And so that's why it's just u, right? So 4 times u. The only one that we have to deal with is the v to the -4, right? And then take the square root. There's lots of different ways, fancy ways that we could go about doing it. But what I'm going to do is I'm just going to rewrite v to the -4 over 2, right? Just kind of skipping that step of multiplying by 1 over 2, right? Smushing them together right away. And so now I have 4u times v. -4 divided by 2 puts me at -2. We wanted to eliminate all the negative exponents. So then we have 4u over v to the power of 2. Now we're done. Right? Because there's nowhere else that we can go. Sometimes I find simplifying like this can be kind of tricky, right? Because how do you know when you can stop, right? But if you're looking at something like this and you're saying, well, there's nothing else I could do, you could keep moving the v squared up and down, but that's not going to change anything, right? -2, +2, right? So that's when you're done. Later on, when things get a little bit more complicated, it's going to be hard to know because you could always rearrange things. You can always rewrite it and manipulate it a little bit. So then I'll be more flexible, right, on simplifying. But this is definitely simplified. Okay, any questions about that one? So there are a lot more to practice, but for now, that's all we'll talk about. That's all we'll ever talk about. No. Rationalizing the denominator is, well, you have it in front of you actually. If you've got a root in the denominator, right, so in the bottom of your fraction, then a lot of the time we want to get rid of that root, right? And so we need tools to be able to figure out how can we get rid of that root. And so, well, if you've got something simple like 1 over a, right, we use that trick of multiplying by 1, right? We pick a convenient 1. For example, if I want to get rid of the square root of a in the bottom here, right? I don't care if there's square roots and things up top. I only want to make sure that I don't have one in the bottom. And so what I do is I can say, well, I'm just going to multiply this by 1. But then I'm going to replace that 1 by the root a over the root of a. That's 1. So this one was replaced by root a over root a. But now that I'm multiplying these fractions, right, I've got 1 times the root of a makes root of a, but I've also got the root of a times the root of a. It sounds like a song. Root of a times root of a times root of a times root of a, root of a, root of a. Root of a times root of a. Hitting the charts is a. Right? Mostly because you've got a to the 1/2 times a to the 1/2. That's a to the power of 1/2 plus 1/2. 1/2 plus 1/2 is 1, right? And so you can always bring it back to those exponent rules. What if you've got something trickier in the bottom? So now you don't just have the root of a, now you've got the nth root of a to the power of m. As long as, and it's got this little note that m has to be less than n. The only reason for that is if m is greater than n, then you should probably simplify it a little bit first, right? But other than that, it doesn't matter. So then instead of multiplying by 1 as the root of a over the root of a, now your 1 is going to be the nth root of a to the n minus m over the nth root of a to the power of n minus m. And the reason for that is once you multiply those in the denominator, right, then you have the nth root and the nth root, which means that we can combine those all under the nth root, right? So that's what we've done here. But it also means that we've got a to the power of m times a to the power of n minus m. So we can combine those as a to the power of m plus n minus m. M plus n minus m, yikes, they're similar, is just going to be n, right? So now we're taking the nth root of a to the power of n, but that we know is going to be a, right? So it's a little bit harder to think of this value as making our value of 1, right? But that's how we have to do it. So once we've got a fraction where there are no radicals or no roots in the denominator, we say it's in standard form. So that's just terminology. I'll steal some of these. Because let's see here, which one should we do? How about 82B? That might be the hardest one on here, I think. So remember, the goal is to get rid of this 6th root on the bottom. You can have roots and stuff up top, but the goal is to not have any roots on the bottom. Right? Ideally, just a b or a b squared or something like that. So we've got 82b is a over the 6th root of b to the power of 2. And we want to do whatever we can to get that 6th root of b squared to be just nothing with a root. And so what we do, we'll start and say, okay, well, that's going to be the same as a over the 6th root of b squared times 1. Right? Just kind of starting off slow because that's what we're going to have to do, right? And then we say, okay, well, I'm actually going to steal this here. Because for now, it's all new, right? And so we want to just have little notes with us while we're learning. So that 1, right, is going to take the place of n root a to the power of n minus m, right? So original had the shape, the nth root of a to the power of m. Oh, turn my m into a halo. Woo. It's a very good a. So in our case, right, if we have to match this original, right, to the 6th root of b squared, well, then my n is 6 and my m is 2. Right? And so here, let's use a different one. N is 6 and m is 2. Right? So this is going to be a over the 6th root of b squared times, and this is where I have to take, and maybe I'll do just the n and the m for now. So the nth root of a to the power of n minus m over the nth root, so same thing over, nth root of a to the power of n minus m. And now I'm going to plug in my n and my m, right, that I determined from the denominator that I want to get rid of. So this is a over root 6b squared times n is 6, so still the 6th root of a to the power of n, which is 6, minus m, which is 2. Over the 6th root, so same exact thing, a to the power of 6 minus 2. Whew. All right. Now, it's going to go from looking nasty in the bottom to looking nasty on the top and nice on the bottom, but that's what we wanted. Uh-oh. Low battery. Which one's complaining? It's this one. The main event. We don't have that much time left, do we? But who's counting, right?
1 minute for every percent.
Yeah. All right. Okay. You can do it. So now on the top, right, I'm just going to write a times the 6th root. So I'm just going to combine these, right, because I'm multiplying fractions, so I can just multiply across. A times the 6th root of a to the power of 6 minus 2 is just 4. So I'll leave that for now. The nice part about fractions is that you can simplify on the top and you can simplify on the bottom, and you can do it kind of simultaneously as you move along. Question?
Why are we multiplying it by by a instead of b in the n root?
We're not. Good catch. Dun, dun, dun. This I was just using the formula blindly, wasn't I? I want to use the same base here as here, right? And so the original formula uses A, but we've got a base of B. And so we want to use B here and B here. Thank you. Perfect. I'm still at 10%, so it's like nothing ever happened. And I can cheat like that. Now I have to replace them. B, 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 B. Good. Oh, what a mess that would have been if you hadn't caught that. Yikes. Yeah. But now, in the denominator, right in the bottom, I've got the root of 6 times the root of 6, so I can combine those all under the root of 6, and I can simplify and see what happens. So now I've got the root of 6 on the outside, b squared times b to the power of 6 minus 2 is 4 still. So now I've got a times the 6th root of b to the power of 4 on top. And then I've got the 6th root of b to the power of 2 plus 4, but I'm just going to write 6. The 6th root of b to the power of 6 is just b. So that was the whole goal, right? And so we've got a times the 6th root of b to the power of 4 over b. And that's good. We could probably simplify the 4 over 6, but I'll leave it for now. Wouldn't actually change anything, right? We would still be taking the root of b to the power of something, right? Because we could simplify it to 4 over 6, but 4 over 6 is 2 over 3. It doesn't really change anything. So I'm going to choose not to. All right. Any questions? So for next day, because I'm a chatty Cathy and we can't seem to get through these things, you have everything that we're going to go through next day, so 1.3 and 1.4. And what I want you to do is read through all these and try some of the problems because they're in here now, right? And so try some of these problems, and then on Friday, let me know which ones you had trouble with, and we'll focus on those. How about? Okay. Otherwise, we'll just keep going with the next few sections. So hopefully you'll have some questions. All right, any questions? Cool. See you guys on Friday. In the portables, always changing venues. 8%, acres of time.
If we try that one problem at home, how we come to know that answer is correct or not?
Oh, it's from the textbook, and the textbook is on WebAssign, right? So there's the ebook,
Okay.
and so it'll be able to show you the answer. Yeah.